Hello everyone. In this video, I want to show you how to look at the frequency content and specifically magnitude of a discrete composite or harmonic signal. So here you have a sine wave, discrete sine wave, and this one has it can have several frequencies in it. And here you can see I picked 15 and 40 hertz, but you can pick whatever you want. And the amplitude I pick for them is 1, and the offset I pick for them is 0. You can even just type in 0 here, okay? So just something like 1 sine of 2 pi 15 or 30, basically pi t. And another one is plus 1 times sine of 80 pi times t, and no phase. You can see that the signal is discrete, not continuous, and the computation method is true trigonometry function, not lookup table or anything. Since it's a discrete signal, you have to give it the length of the signal. Here is 128 numbers and a sample time. Okay, so this is your sine wave, which comes from the DSP or digital signal processing signal. And when I want to get the frequency content, I have to use Fourier transform. So here I use the FFT block, and this FFT block is for a single or scalar signal, basically. Okay, and the method I used auto. And so since it's a single or scalar signal that needs to go in, and the signal that is coming out of this DSP has 2 dimensions, right? It has 2 frequencies in it. So here I use this block called the matrix sum, and this one will add, you give it the dimension of the components in the signal, and it is going to add them together and make them a single. So this one has 2 separate signals. This one is sum of the 2. So now it's 128 by 1. It goes to FFT, comes 128 by 1, but complex numbers, as you know, when you apply Fourier transform, the result is a complex number. And since I want to look at the magnitude of it, I use this block here. This block here is called complex to magnitude angle. This is another block in Simulink, and you can pick the output to be either magnitude or angle or both. Here, I just want to look at the magnitude. And then before I send it to this block that is called the ArrayPlot, and this is a specialized block in DSP that can give you the magnitude of the signal. You can even add the phase of it if you want, and you can highlight the peaks of the signal, which are the place that the frequency exists. You can perform measurements. So this is a powerful block, and this has more stuff to it than a simple scope, basically. And this is really good for looking at an array. So here, now you see that I'm looking at 2 versions of it. One, directly the magnitude of the complex number coming out, and I look at it, which shows magnitude versus frequency. The other one, I apply this block called FFTSHIFT. And if you look at it, this is a basically MATLAB function, and since that block alone does not exist in Simulink, so here is a customized or MATLAB function where the output is the FFT shift of the input, and I use a shifted frequency version of the magnitude, and I plot it on ArrayPlot as opposed to ArrayPlot 1. And you might say, what's the difference between these two? What is the shift doing? I'm going to explain all of that, okay? But right now, let's just see what the result is before I explain the thing behind the box. So remember, the magnitude of the signals both are 1, the frequencies are 15 and 40 hertz, and they don't have any phase, okay? Yeah? So when I look at the frequency content, I should see 2 peaks, one at 15 hertz, one at 40 hertz with magnitudes of 1 in the magnitude plot. So let's go ahead and run, see what we get. Okay, this is array phase plot 1. This is this guy here that did not use the FFT shift. Let's look at it again. And what do you see here? You see there are 2 peaks here, and then you see there are 2 other peaks here. And if you look at these peaks, they are exactly the mirror image of each other with respect to the center. So if one of them are like F1 and F2, the other ones are negative F1 and negative F2, okay? And first of all, their magnitudes are not 1. They are like 64, 65. The other thing is, if you look at the frequencies, okay, if you look at where the frequencies are happening, so here, this is P3, this is P1, look at them. P1 is at 484 hertz, and then the other one is at basically 460 hertz. And you might say, well, they're supposed to be like 15 and 40. What happened? All of a sudden, you're at 460 and 484. Now, look that the difference between these two signals is about 25 hertz, which is the same difference between 40 and 15. But clearly, they are way shifted. They are like about 445 hertz added to the actual thing. So they are shifted to the right. And this is the nature of FFT, okay? But if you look at the other one, that is this phase array with FFT, look what you have. Again, you see the same 4 peaks, and again, they are mirror image of each other, right? So F1, F2, negative F1, negative F2, but look at them. Look, this is at 15.6 hertz with magnitude about 64, and this one is about 39 and 63. So first of all, you see that the frequencies are very, very close to the one that used to be, right? So of course they were 15 exact. This is 15.6, and this one was 40. That was not this 39.1 or something. So the frequency is almost correct, but the magnitudes are not. One of them is 64, one of them is 63. So why is it that the magnitudes are not 1? Because the magnitude is supposed to be 1, huh? So what's going on here? Let me explain that. Let me explain why the magnitudes are not 1, and let me also explain why you need this FFT shift so you can see the frequencies properly. Okay? So here I need to explain that to you. So first of all, what happens when you take the fast Fourier transform or Fourier transform of a discrete signal? So here, the signal I have is a sine wave, right? Each one of them is a sine wave. And as you can see, if the length of the signal is n, and if k is the frequency content of the signal in hertz, then the signal can be written as x of n could be written as sine of 2 pi k naught over n times n, where this small n changes anywhere from 0 to n minus 1. And again, this k naught is your frequency in hertz, okay? So this is your discrete sine wave with a length of n and with frequency of k naught in hertz. Now, you know that the Fourier transform is when you apply the signal, you plug it into this formula, right? So you multiply the signal by a negative exponential, which has complex component, and it takes you from the discrete signal n, where n is kind of corresponding time, to the capital X with content m, where m here is the frequency. So this m is in hertz, and this n is in seconds, okay? So this take you in other textbook, you see that this x is written as a function of f, and the small x is written as a function of time, but that is for continuous signals. Since you have discrete signals here, we are changing them with m and n, okay, just indices. And since the signal is limited, instead of integral, you have a summation that goes from 0 to n minus 1. And so this is your discrete Fourier transform, or DFT. And FFT is a method of applying the discrete Fourier transform, but just a fast version of it, right? So FFT is fast Fourier transform, DFT is discrete Fourier transform. And FFT, again, is a mathematical implementation of that. So this is what we are doing to the signal here, look, when we apply this DFT, right? Okay. So since this guy has exponential, I'm going to write this sine wave also as exponentials, because then you have exponential times exponential, which end up being another exponential, and performing the summation is easier. So what I'll do here is I write the sine as basically 1 over 2j e to the jn minus e to the negative jn, right? You all know that a sine of x, based on the Euler equality, can be written as e to the ix minus e to the negative ix, and then divided by 2j, and j is the base of complex numbers. So here we are using the exact same thing, and we write that x of n like that, and we plug it exactly here. And then this exponential, this one is multiplied by this, and then this one is multiplied by this, and you're going to get this. Okay. Now here we're going to calculate each one of these two summations and simplify this. Now you know that e to the 2j pi r, as long as r is an integer, the result of this is always 1, correct? So whether it's 2 pi j, 4 pi j, 6 pi j, negative 4 pi j, all of them are equal to 1. So if you look, considering this knowledge that we have and the result that we got for x of m, I can say that a summation like this, which is similar to both of them, this is equal to n if this ratio r over n, if this mode is 0, which means this is an integer, this is like a multiple of that, so it's like 2, 3, 4, and n is integer, so you end up with all of that as integer, and since you have n of these terms, you are adding n of ones, you get n. Otherwise, if this ratio is not basically, if this modulus is not 0, then of course this is going to be a geometric series, and you know some of the terms in a geometric series is coming from this. So if you have terms like a and aq scored all the way to aqn minus 1, right? If you add all of this together, you know this is equal to basically a times qn minus 1 divided by q minus 1. Okay, and so that is exactly what you're using here. So depending on whether the ratio of r over n, this modulus, is 0 or not 0, each one of these can be calculated based on this bottom formula. So if you plug them in and simplify, you can see that the similarity between them is this r term here is to be replaced by k naught minus m or k naught plus m. And you can exactly apply this result to those top ones. So if you do that and simplify with a little bit of complex calculations, this is your final simplified signal. X of m is equal to n over 2j, you can bring this n out if you want, n over 2j of a delta function minus another delta function. And this delta function, you know, this is the canonical delta. So the value of it is 1 at that location, and elsewhere it's 0, and the same thing for this. So what kind of shape does this one have? Well, this has two peaks, right? One for this, one for this. And where are those peaks? One of them is at k naught. The other one is at n minus k naught. And what's the magnitude of them? The magnitude is what? N over 2j for the first one, and negative n over 2j for the second one. Okay? So these are the magnitudes, and the magnitude of both of them are n over 2, right? The magnitude of both of these signal is n over 2 here. So what you will see for this signal, if you look at it in the frequency domain, at the frequency of k naught and then n minus k naught, if this is the frequency and this is the magnitude of x, you should see two peaks, one like this, one like that, and the magnitude for both of them is n over what? N over 2. Okay, so this is the Fourier transform or discrete Fourier transform for a sine wave that was something like sine of 2 pi k n over n. Okay, so this is the Fourier transform of that. The frequency was k naught in hertz. So first of all, for that k naught, you're going to get two peaks, not only one peak, you're going to get two peaks. And the magnitude that the peaks are n over 2, they are not 1 or anything. Although this magnitude here was 1 times sine, but the magnitude you see over there is n over 2. So if I go back and talk about this, what magnitudes do I have here? The sample, the length of the signal. What length of the signal I have? 128, right? So in my case, this n is what? This n is 128. So the magnitude I should expect should be what? 64, which is 128 divided by 2. And was that 64? Yes. If you remember, the magnitude that you got out of here was 64, about 64. Look, it's 63. And this one is what also? About 64, 63.98. So that justifies why the magnitudes are 64, not 1. It also justifies that why you have 2 peaks for each one and not 1 peak. Correct? If you look at either one, remember you have 2 peaks, right? You see here you have 2 peaks and you have 2 peaks. So the last question is, what does this FFT shift do? Right? Why the result of these two are different, although they have basically the same magnitude. The magnitude on both of them is about 64, but the frequency are different. This one shows proper about 15 and 40. This one shows each one of them shifted way to the right, like 400 units to the right. Where does that one come from? So here is the explanation. So when you apply FFT on a discrete signal, remember I told you the y-axis is going to be n over 2 for a harmonic. What happens to the x-axis? What kind of result would you get out of the x-axis? So the x-axis is going to be this, that the sampling frequency that you have, okay, if Fs is your sampling frequency, remember in our case, the sample time, delta t, is 0.001. That means the sampling frequency is 1 over that, which is 1,000 hertz. So the range that you get on the frequency axis is going to be what? At frequency of 0, you're going to get 0 hertz, of course, corresponding to being index 0. Then what? Remember, the length of your signal was what? It was n. So your data goes from 0, 1, 2, all the way to n minus 1 when you had this signal, correct? This is how your n would change. Now, corresponding to these discrete numbers, what kind of frequencies would you see on the f-axis? So 0 is 0. Then for 1 to n over 2 minus 1, the range of frequency you'll see is all the way to the sample frequency over 2, which in this case is about 500 hertz. And then from the midpoint of that data all the way to the end of the data, you are going to go negative frequencies to negative Fs over 2, which is negative 500. So this is the range of the basically frequencies that you would be shifted. Okay, now this is if you have 0 frequency. If you have 15 and 40, you will get an extra shift. Okay, so as you can see here, that makes everything to be shifted by about something like 500 units or 450 or something close to that, to the left or to the right. Okay, and that is what exactly you saw here in this plot. If you look at it, instead of the frequencies be here at around 15 and 40, they are way shifted close to like 500 or something. Okay, so the fact that they are all shifted by Fs over 2 to the left and to the right, so instead of negative 15 and negative 40, they are like negative 400 something close to 500, and so both and positive that number. This is because of the way that the FFT command work. So what does the FFT shift do? The FFT shift says, no, I'm going to limit the frequency for you and get rid of this shift. So I make sure that you are exactly centered around 0. And although you can go to FS2 and negative FS2, but you don't have that extra shift here. And that is what you can see in this one with the FFT shift. Let's look at it. This one does not have that shift. Look, you can clearly see that. Let me zoom out so you can see that better. You can clearly see this one, the frequency is at about 15 hertz, 15.6, and about 40 hertz, and these are the negative of those numbers. So this one will get rid of those big shifts to the left and to the right, which are by about Fs/2. So if you want to see the frequencies properly, make sure you apply FFT shift on the frequencies, then you do the plot. Otherwise, this one is going to be wrong. Okay, so now that you have seen the frequency content and you find that what kind of frequency exists, and from these magnitudes of 64, 65, if you compare that against 128, you could tell that, hey, the magnitude was really what? 1. Because if this magnitude becomes 2, what do you think will happen? If I change both magnitudes to 2, what will happen to the things that you see in the FFT? Let's run it. So you expect them to be 2 times 64 this time, huh? So this is the one with proper FFT shift, and look at that here. You see? The magnitude is now about 126, and this one should about 128. The same frequency, 15 and 40, but the magnitudes are doubled. So now, since the magnitudes here are 128 and the length of the signal is 128, I expect the amplitude to be 2, because remember, here we have n over what? N over 2 here. Or if the signal here, let me put it this way, if the signal here is, let's go down 1 second. If the signal here is like A times that, okay, if this signal is A times this, the magnitude you'll get in the FFT is A times n over 2. So clearly you can find A. Okay, I'm gonna share with you this Simulink file under video description. Feel free to play with it and learn from it. But this is how you can see the frequencies and their magnitude in a signal. And if you want, you can get the other one here and change it to phase, and you can look at the phase as well here. But here my goal was to just explain the differences that you see in these plots and what you put in this block here. Thank you so much for your attention, and I'll see you in the next video.